So we did electron affinity and we are going to continue electron affinity. Electron affinity means it's the reverse of ionization energy. Okay. Ionization energy was when something loses electron. Okay. So electron affinity means that when something gains electron. So let's say if we have an oxygen atom, okay, oxygen would be gaining 2 moles of electron. Generally, the charge on oxygen is -2, right? So when the charge of oxygen is -2, so I can say that it would be gaining 1 electron first. It would be having negative charge, and then it would be gaining its another electron. So it would be having -2 charge. Okay. The thing is that the definition of electron affinity is when 1 mole of an atom in gaseous state. In ionization, the condition was same from the gaseous state. And today in electron affinity, the condition is same. When 1 mole of an atom is going to gain electron, it should be 1 mole of electron, okay, to form 1 mole of a gaseous anion. Of course, when something will gain electrons, so it would be forming -1 ion. It's called anion. So the energy is released. It's an exothermic system. When something gains electron, it's an exothermic system. Okay. But what if oxygen is going to gain second electron? When it has gained first electron, so it got a negative charge. What if it's going to gain its another electron, like second electron? Since they both are having negative charge, as we know that like charges are going to repel each other. Okay, like charges are going to repel each other. In order to overcome the force of repulsion, in order to overcome the force of repulsion, you have to provide energy. In order to overcome the force of repulsion, you have to provide energy. That's why we can say that electron affinity is sometime exothermic and sometime endo. Sometime means that first electron affinity is exothermic and second electron affinity is endothermic. Okay. First electron affinity is exothermic and second electron affinity is endothermic, and that's the reason. Why second electron affinity is endothermic? In first electron affinity, oxygen was neutral, so it has gained 1 electron and energy is released. But in second electron affinity, oxygen is already negative. So to overcome the force of repulsion, energy is required. When the energy is required, so therefore second electron affinity is endothermic. He would be asking this, okay? He would be asking this one. So let's say phosphorus. Generally, phosphorus is going to have -3 charge. Generally, phosphorus is going to have -3 charge, right? So what it would do, first of all, it would be gaining 1 electron to form P-1. Then it would be gaining another electron to form -2. Then it would be gaining its third electron to form P-3. One by one, one by one. So of course, when it would be gaining first electron, so that's gonna be exothermic, of course, okay? And when it would be gaining another electron, so it would be endothermic, and when it would be gaining the third electron, again, I can say that it would be endothermic, okay? Uh, then what are the factors? What are the factors on which electron affinity depends? What are the factors on which electron affinity depends? So remember, these are the factors: nuclear charge, atomic radius, and shielding. Nuclear charge, atomic radius, and shielding, right? So these are the three factors. I can summarize it. Nuclear charge is directly proportional to the electron affinity. Let's say fluoride and iodide, like fluorine and iodine. which can gain electron more easily? Of course, fluorine. Why? Because fluorine is going to have smaller radius, stronger nuclear charge. It can gain electron more easily as compared to iodine. As we can say, iodine has a greater atomic radius, weaker nuclear charge. So electron affinity of iodine would be lower. Okay, so depends on the size, depends on the nuclear charge, and depends on the shielding. Shielding means repulsion between inner electrons. Shielding means repulsion between inner electrons, right? So inner electron, like I can say, let's say fluorine is going to have only three shells. Sorry, two shells. One, two, three, four, five, six, seven. Right? This is an electronic structure for fluorine. And when you will be making iodine, so I would be having 4 to 5 shells. If I remember, iodine is in period 4 or period 5. Period number is going to represent the total number of shells, right? So when the number of shells are higher, so the shielding effect would be higher. When the number of electrons are higher, so the shielding effect would be higher. When the shielding effect would be higher, so means that due to the repulsion between electrons, the atomic radius of that particular element would be higher. When the radius is larger, so it cannot gain electron more easily, of course. So electron affinity would be lower. So it's all about these three factors. Okay. Okay. Then we have standard enthalpy change of ionization. Always we talk about the standard conditions. That's why again and again we are going to say 1 mole, 1 mole, 1 mole. Energy is required. Like if you remember in unit 2, when we used to discuss atomic structure in that chapter, also we did this ionization energy, if you remember. So we used to say that energy required to remove electron from the outer shell of a gaseous atom, isn't it? Okay, energy required to remove an electron from the outermost shell of a gaseous atom. But now what am I supposed to say? Because this is under standard conditions. So that's why we are saying that energy is required when 1 mole of electron is removed from 1 mole of a gaseous atom to form 1 mole of a gaseous cation under standard condition. The same thing, but again and again we are going to say, like at a time you cannot remove, you can remove, but we are not supposed to remove more than one electron because it would not be a standard condition. Okay, always one by one. Like let's say if we have aluminium, so first of all you can remove first electron, it would be forming Al plus 1. Then you can remove another electron, it would be forming Al plus 2. Then you will be removing its third electron, it would be forming Al plus 3. So one by one, one by one, energy is required to remove 1 mole of electron to form 1 mole of a gaseous cation. Okay, so this is called standard enthalpy change of ionization. Okay, so as you can see, sodium is in the gaseous without converting the sodium solid into the sodium gas, you cannot remove electron. You cannot remove electron. Without changing solid into gas, it's not possible. It's not possible. So before ionization, you need to do atomization. Makes sense. Before ionization, you need to do atomization, and we do. When we would be making a Born-Haber cycle, we will do. Remember, we will do. Okay. So before ionization, we have to do atomization. Once atom is formed, like I'm talking about the gaseous atom. Once the gaseous atom is formed, so I can say that, and now you can remove electron easily. And that's it. Now you can remove electron easily and that's it. Okay. Um, so then we have magnesium. Magnesium is in group 2. We can remove more than one electron. Generally, magnesium loses 2 electron. Generally, magnesium loses 2 electron, right? So it would be forming plus 2. But you are supposed to remove one by one. One by one. First of all, it would be forming plus 1, then it would be forming plus 2. Right? Okay. Or it's always endothermic. Always energy is required. It's not like electron affinity, sometime exo, sometime endo. No. Always energy is required. Always. It's fixed. And it's also known as successive ionization. What is this? Successive ionization energy when something can lose more than one electron continuously. Al, first of all, Al plus, then Al plus 2, then Al plus 3. First ionization, second ionization, third ionization. And we know that second ionization energy is always higher than the first, and the third ionization energy will always be higher than the second. You know why? It's an old topic. After removal of electron, after removal of electron, the size is gonna decrease. Okay, you can ask if you are having any issue. What I'm saying, what I'm saying, uh, after removing one electron, after removing one electron, okay, after removing one electron, the size is going to decrease. When the size decreases, so the force of attraction increases, okay? When the size decreases, so the force of attraction increases. And when the force of attraction increases, so of course, more energy would be required to remove that electron. So that's why I am saying second ionization would be higher than the first. And when the two electrons are removed, so the size would become smaller. So the size would become smaller, okay? And when the size would become smaller, attraction would become stronger. So to remove the third electron, more amount of energy would be required then. So I can say that ionization energy would be higher. So as the number of electrons are going to increase, so the ionization energy increases. That's the concept. Okay. Or okay. Then now, after discussing these all the things, I am going to form a Born-Haber cycle. That's the extension of Hess's law. Advanced form of Hess's law is Born-Haber cycle. Criteria is same, concept is same. We used to say that the product of the reaction is independent of the route taken. I need product. I don't care which path you are going to select, which path you are going to opt. I need carbon dioxide. Whether you are going to form carbon dioxide directly after the reaction of carbon with oxygen, and whether you are going to form carbon dioxide by using carbon monoxide. First of all, you have reacted carbon with oxygen to form carbon monoxide, then carbon monoxide would react with oxygen to form carbon dioxide. It's a two-step reaction. Whether you can do two-step reaction and whether you can do one-step reaction, in both cases, carbon dioxide would be formed, and in both cases, the same amount of energy will be released. Remember, there would be the same amount of energy. Whether you are going to do direct method, whether you are going to do indirect method, amount of energy would be the same. Okay, so same criteria with the Born-Haber cycle, but diagram is something different. Like the Born-Haber cycle is something different as compared to the Hess's law. So what is this? Uh, Let me tell you this one. Let's say, I want to draw the Born-Haber cycle for, I can say, the sodium chloride. Okay, so you can see this. I'm going to start sodium solid will react with chlorine gas. It would be forming, it would be forming sodium chloride. sodium chloride solid. It would be forming sodium chloride solid. Okay. This is called enthalpy change of formation. I'm going to balance it. I'm supposed to write half. You are not supposed to put any number over there because we have discussed that. What was enthalpy change of formation when 1 mole of a compound is formed from its elements in their standard states under standard condition? Okay. So I can not write any number to balance this equation because we must have a 1 mole of a product. That's it. Then what am I supposed to do? Then I'm going to do it indirectly. How? Uh, I'm going to convert this sodium solid into sodium gas. I'm not touching chlorine right now. I'm only solving sodium, right? After solving sodium, then I would be uh, dealing with the chlorine. Okay. First of all, right now I'm going to convert that sodium solid into the sodium gas. What's the name of the process? It's called delta H of atomization. Since atomization is endothermic, I'm going to draw an arrow upward. I'm going to draw an arrow upward. Remember, if the process is exothermic, so we are supposed to make a downward arrow. And if the process is endothermic, then we are supposed to draw an arrow upward. It's the concept. Okay. And then, uh, okay. Mm, okay. Um, it's called atomization. Then after atomization, what am I supposed to do? What am I supposed to do? I have to ionize it like from sodium to sodium positive. As it is, chlorine remains same. This is called this is called ionization. This is called ionization. Okay, right? And then sodium is ready. Sodium is ready, right? Sodium is ready. I'm gonna work at chlorine. I'm gonna work at chlorine, It's a chlorine molecule. I have to convert in a chlorine atom. This is called again atomization. Again atomization. In that process, I have atomized chlorine, sodium, and now I'm atomizing chlorine, the same thing. So it's always endothermic. So I put an arrow upward. Then you can see uh, plus chlorine minus. What's this? What is this? Chlorine minus. Before it was zero. There is no charge, means this is zero. There is no charge, means this is zero. 0 to minus 1, it's gaining electron. 0 to minus 1, it's gaining electron. When it's gaining electron, it would be called electron affinity. And first electron affinity is exothermic. First electron affinity is exothermic. That's why I put an arrow downward. That's why I put an arrow downward. Okay. So then now they are ready to combine with each other. Since the cation and anions are formed, they are ready to combine with each other. They will combining with each other to form they will be combining with each other to form what? To form the sodium chloride. Exactly. This is called lattice energy. So I can say that In this one, I have formed sodium chloride directly. And like this one, also I have formed sodium chloride. Also I have formed sodium chloride, but but indirectly. So the concept says direct route is equal to indirect route. Direct route is equal to indirect route. That's called the Born-Haber cycle for sodium chloride. Try, you can try the Born-Haber cycle for magnesium chloride. You can try this. Then I'm going to show you how I drew the Born-Haber cycle. Yes, Iman.
Sir, how do we know what are we supposed to do next?
How do we know what?
Uh, like,
How
how
do
do we
we
know
know?
what are we supposed to do next, like one after other?
First of all, we have to work on a metal, then we have to work on a non-metal. And when you will be working on a metal, of course, you have to convert the metal into the cation. In the end, I need to do this. I need to have these things. In the end, I need to have this thing, right? So positive and negative will be attracting together to form an ionic compound. So how did you get the cation and anion? We are going to work on it. I have the metal. I'm going to convert it into the sodium gas. Like I'm going to atomize it. Once it is atomized, then this atomized, like this is an atom, which will be gaining one electron, which will be losing one electron to form Na positive, like it's going to be ionized. Okay. Now Na plus is ready. Now Na plus is ready, right? Like this one. This is going to be ready. It needs a Cl minus so that they can react with each other to form a sodium chloride. Okay. So this is called ionization. Now the metal is completed. Goal is achieved. We uh, want to convert that particular metal into the cation, and we did this. Now we are working on a non-metal. Like in some questions, the non-metal is chlorine. In some questions, the non-metal is bromine. It may be iodine. It may be oxygen. It may be nitrogen. It may be anything else. Then what I'm going to do? This is a molecule. I'm going to atomize it because without atomization, it cannot gain electron. It cannot form an anion. Concept. It's a concept. It cannot form what? An anion. Remember, until or unless you are going to atomize it. So I have atomized it. It has converted from the molecule to the atom. Then it has gained one electron to form an anion. It's called electron affinity, which is exothermic. Then they will be attracting together to form sodium chloride. This is called Born-Haber cycle. So it's a step-by-step process. First of all, you are supposed to work on metal, then non-metal, and then you're going to solve it. So what do you think about magnesium chloride? I'm going to give you only 1 minute. I have done this. I'm going to show you this. If your working is matched with my, so that's good. And if not, then you have to see your mistakes. Okay, start. You have only 1.5 minutes. Fast. I'm going to show you this one, magnesium chloride. You are supposed to match it with your structure. Okay. This is the Born-Haber cycle for magnesium chloride. I did aluminium, the same thing. Aluminium is in group 3, magnesium is in group 2, of course. It would be longer than magnesium chloride. Since aluminium is going to have a +3 charge. Manal sent me the Born-Haber. Okay, let me check Manal. Okay, okay. It's not downloading. Okay, let me see. So what I did, you can see, first of all, the same thing as I have started from the delta H of formation. Yeah, I can see this one. Manal, magnesium solid to gas to +1 to +2, then Cl2 to Cl minus. Okay, good, Manal, good. Okay. So Al solid, then it would be converting into gas, then +1, then +2, then +3. Then bromine, it turns into gas, then atom. So first of all, I have worked on a metal, then I'm going to work on a non-metal. Okay, you have to convert this fluorine into the bromine into the bromide. Once the ions are formed, once the ions are formed, okay, once the ions are formed, so they will be reacting with each other. They will be forming aluminium bromide. That is called Born-Haber cycle. That's very easy. That is called Born-Haber cycle. That is very easy. Okay. Can you solve magnesium oxide? Magnesium oxide. Also, it's an ionic compound. In magnesium oxide, magnesium is +2 and oxygen is -2. How the magnesium is converted into Mg +2 and how the oxygen is converted into O -2 when they will be having a charge, when they will be having, um, let's say, um, magnesium in magnesium oxide. First of all, you have to convert it into Mg gas, then Mg +1, then Mg +2. And oxygen means that first of all, you have to convert it into the gaseous state, then O -1, then O -2. Electron affinity twice, ionization energy twice. So it's a longer diagram. Okay. You can try this, then I'm going to show this. Yes.
Sir, since oxygen is -2, how am I supposed to make the ion?
Okay. This is magnesium oxide. You can see the Born-Haber cycle for magnesium oxide. First of all, I have converted solid into gas. Okay, once the solid is converted into gas, then I can ionize it twice because Mg is going to have +2 charge. Okay, so this is called second ionization. And then oxygen is a molecule. I have to convert it into in the gas. It's called atomization. Once it has converted into an atom, then what am I supposed to do? O2O minus 1. Since oxygen has a -2 charge, since oxygen has a -2 charge, so we have to do electron affinity twice. In the first electron affinity, it would be converting from 0 to -1. And the first electron affinity is exothermic. So that's why I'm going to put an arrow downward. But we have learned that second electron affinity is endothermic. So then -1 to -2, then we have to make an arrow upward since this is an endothermic. Then once the ions are formed, they would be attracting together. They would be forming magnesium oxide. That is called lattice energy. Got it? Okay. Yes or no? Huh?
Yes, sir.
Okay. Then the kind of, I can say, the difficult Born-Haber cycle is magnesium nitride, Mg3N2. Okay. Magnesium would be having +2 charge. Nitrogen would be having -3 charge. So you have to do an electron affinity thrice. Thrice. First electron affinity, then second electron affinity, then third electron affinity. Mhm. Okay. Let let me show you this one. Let me show you this one. Uh, Aluminium oxide, right? Hmm. Aluminium oxide, I didn't draw. Okay. It's aluminium bromide, it's magnesium oxide, it's aluminium nitride, magnesium bromide. Okay. So you can see this one. You can see this one. The same criteria. Same criteria. Nitrogen. First of all, 0 to -1, arrow downward since this is an exothermic. -1 to -2, second electron affinity. -2 to -3, third electron affinity. Third electron affinity. Okay. So when I would be having the third electron affinity, it would be most endothermic. Okay. Once the ions are formed, so they will be reacting together. They will be forming ionic solids. It's called lattice energy. Okay. Simple and then again simple. Hopefully you are getting my point, what I'm saying to you. So basically you have to take care it which type of ion you have. It's in group 1, it's in group 2, it's in group 3. What is this? What type of non-metal you have? Is this have a -1 charge or a -2 charge or a -3 charge? Because then we have to decide accordingly. Then we have to do the work accordingly, right? Sometimes we go upward, sometimes we go downward because we know that first electron affinity is exo. We are supposed to move downward. Then the rest of the electron affinities would be endothermic. Then we have then we have to move upward. It's all about the concept. It's all about the like prior knowledge that you know about that or not. Okay, on the basis of that information, you can do like you can draw the Born-Haber cycle. It's not so much difficult. It's not so much difficult, but only first of all, like Iman was asking that how do we know that which steps we are going to follow one by one? It's nothing basically. The criteria is this: we are going to work on a metal first. Once the metal is converted into the cation, then we are supposed to start the non-metal, and until or unless the non-metal is converted into the anion. Once the ions are formed, so they will be attracting together to form ionic solid, or that's it. Okay, it's easy. It's very easy, right? So rest of the things I can say that the values would be given to you. Okay, the values would be given to you. Like I can say in this question, you can see use the following data together with the relevant data from the data booklet to calculate a value for the lattice energy of strontium chloride. You may find it helpful to construct a Born-Haber cycle. Some values are given to you and some are not. Some values are given to you and some are not. So, so the unknown values you can see from the data booklet. The unknown values you can see from the data booklet. Okay. Like they have given you atomization of strontium. Okay, it's good. They have given you the, they haven't given you the atomization of the chlorine molecule because because what is this? Is it's strontium chloride, SrCl2. So of course you need to know electron atomization of chlorine as well. So we can see the data booklet. Okay. So unknown values we can see from the data booklet. Then you have to draw the Born-Haber cycle like that. It's not magnesium chloride, it's strontium chloride. The same thing. They are in the same group, right? They're in the same group. They are in the same group. So the criteria would be the same. Just what you have to do in this, we have to put all the values, of course, in the whole equation. One thing would be unknown. Rest of the things are given to you. So you can just put the values and then you can find out the unknown one. That's it. Again, I'm saying it's easy. If you know the concept, if you know what we are supposed to do first, then what we are supposed to do second, so everything will be fine. Okay.